Unified dynamics.
When we picture an atomic nucleus, we usually imagine a vibrating liquid drop or a fuzzy cloud of quantum probability. But strip away that haze, and the math suggests a very different reality. The Unified Dynamics framework asks a specific question. What if atomic nuclei are not chaotic blobs, but rigid, mathematically precise geometric structures? To see how this works, we start with the alpha cluster, helium-4. This nucleus has exactly 4 components, 2 protons and 2 neutrons. Geometrically, any arrangement of 4 equal points locks into a stable tetrahedron. With a physical shape as the building block, structural architecture dictates atomic stability, replacing the standard model's reliance on abstract energy levels. To build heavier elements, nature must stack these tetrahedral blocks together, and immediately the laws of mechanics take over. Take 2 tetrahedrons, join them end to end to make beryllium-8, and you create a fragile one-dimensional line. The mechanical leverage is massive. Under its own torque, the nucleus snaps apart. Adding a third block creates carbon-12. These 3 pieces lock into a flat, 2-dimensional plane. It is far more stable than the line, but it still lacks volumetric depth. When a 4th block is introduced, it cannot fit into that flat surface. To optimize the connections, the 3 existing cells tilt upward, and the entire structure folds into a 3-dimensional regular tetrahedron. This is oxygen-16. By pulling the mass tightly toward a central coordinate, this arrangement minimizes its surface area and locks the nucleons into a hyperstable sphere. This oxygen-16 bedrock provides the mandatory scaffolding for every heavier element in the universe. If oxygen-16 is hyperstable, you might assume atoms can keep stacking these blocks forever. But as the universe tries to grow heavier, it hits a mathematical roadblock. This is the geometric packing frustration hypothesis. The problem is that regular tetrahedrons physically cannot perfectly tile 3-dimensional space. Every regular tetrahedron has a fixed internal angle of 70.53 degrees. Pack 5 of these around a shared edge, and their angles only sum to 352 degrees. They don't complete a full circle. You are left with a permanent, unresolvable gap of 7.36 degrees. Because of this tiny, unavoidable geometric gap, the seamless growth of large atomic structures is a mathematical impossibility. In a small atom, a slight geometric stretch is manageable, but in ultra-heavy elements, that 7-degree gap becomes a fatal vulnerability. Atomic stability relies on the strong nuclear force. This force acts as a powerful glue, but its range is extremely short. It requires the flat faces of the tetrahedrons to be perfectly touching to maintain a bond. Scale this up to uranium-238, which contains nearly 60 theoretical blocks. Those tiny angular gaps rapidly compound, forcing the outermost layers to stretch and warp. At the same time, the long-range electrostatic Coulomb force is constantly pushing every proton apart across the entire volume of the atom. This creates the decoupling threshold. The compounding geometric gap forces the faces far enough apart to kill the strong force, leaving the atom held together by an unstable, compromised seam. This structural strain leads directly to the uranium snap. With the internal seam stretched to the limit, even the tiniest vibration from a neutron causes the geometric fault line to completely unzip. While fission is often viewed as a random event, here it is a predictable mechanical failure driven by that 7.36-degree geometric deficit. The evidence is in the fragments. When uranium-235 splits, it shatters asymmetrically into barium and krypton, producing one chunk of roughly 35 alpha blocks and another of 23. This specific asymmetric split maps perfectly to the mathematical fault lines of a frustrated tetrahedral cluster. The break is dictated by geometry, not chance. We see this architectural footprint in the magic numbers of nuclear physics, which correlate exactly with the completion of perfectly symmetrical closed tetrahedral shells. For decades, scientists built massive machines to study invisible forces, unaware they were actually probing the rigid mathematical limits of shape and structure. The absolute limit of the periodic table stands as a hard-coded mathematical boundary of three-dimensional space itself.